In this section, we are going to graph linear equations. Just as the name says, we will be graphing equations that give us lines. We will do so by finding ordered pair solutions. We practiced this in the last section. Here is the definition, or one definition, for a linear equation. The standard form is one arrangement of two different forms. To be a linear equation, it doesn't matter how the equation is arranged, but that the power on the variable is 1. You can have one variable or two, but we'll always need to be thinking in terms of two variables. We did this type of problem in the last lesson. Here, we will take it one step further and actually graph these ordered pair solutions that we come up with. Since the power on the variables are 1, the graph will give us a line. We only need 2 points to get the graph of a line, but we're going to play it safe and always go with 3. If you make a mistake, you won't know it with only 2 points. But with 3, they won't line up, so it'll be obvious that you've made a mistake. Again, here we substitute in for the given variable and then solve for the other one. Once the table is complete, we plot these points. We notice the 3 points line up, so we can assume we haven't made any errors in completing our table. Notice how this line has arrows on the ends to say the line goes on forever in both directions. You will either need to use arrows or extend your line to the edges of your graph paper that will say that your line goes on forever. We only came up with 3 ordered pairs, but understand there are infinitely many ordered pair solutions whose difference is 6. We only worked with integers, but there are decimals and fractions, as well as the integers who would have that difference of 6. There are always infinitely many ordered pair solutions, many points that make up the graph of your line. For this problem, we're not given a coordinate to aid us in the process of finding our ordered pairs. We are on our own on this one. Look at the arrangement of this equation. Being that it is solved for y, it will be easier for us to substitute in for x and then solve for the y coordinate. On the last problem, I commented on the fact that there are always infinitely many ordered pair solutions, or points, that make up a line. So when we pick our x's, it doesn't matter what we pick. So let's pick values that make the work in solving for y easier on us. With a fraction of 2/3 attached to x, let's select values that 3 divides evenly into. I always use 0 for obvious reasons. The other 2 are multiples of 3. Numbers 3 will divide evenly into. I'm trying to avoid coming up with fractions for y. 1, because the math in solving for y will be more difficult, and 2, plotting the points will be a bit awkward. Doable, but not as easy as if the coordinates are integers. Here's our math for completing the ordered pairs. Start by dividing the denominator into x, and then going from there. We've got our 3 ordered pairs to plot, and then, again, draw the line through it. Notice the arrows at the end of my line. We only came up with 3 ordered pairs, since that's all we really need, but understand there are infinitely many possible. Last, let's look at an application that is modeled by a linear equation. When it comes to word problems of this nature, make sure you fully understand what the 2 variables represent, know their meaning and their units. Write this down on your paper to refer to. X represents the number of years past 1983. We'll not put in the year, but rather we'll subtract from 1983. This difference will be what we put in for x. Y is the average tuition. Part A asked us to substitute 0 in for x. If x is 0, this represents no years beyond 1983, therefore it represents 1983. We have found in 1983, the average tuition was $9,202. 1988 is 5 years past 1983. Here we will find that in 1988, the cost of tuition was $11,523. And here we are asked when the tuition is expected to rise to $18,500. Substitute this in for y. X works out to be 20. 20 plus 1983 gives us 2,000.